Brandon Sullivan is going to attempt to spontaneously give a talk called The Convergence of a Random Walk on Slides to a Presentation. So I'm interested to see how this would go. I forgot what his abstract was about, so unfortunately I can't give you guys any more information.
Before I start this particular talk, I just want to point out that in case I didn't convince you well enough last time that the Basel problem is still an active research area, a new proof has been published since that talk a couple weeks ago. And in fact cites the notes that I had written for the talk years and years ago on my website. Oh. It takes
cool.
this alternating series for pi over 4, the alternating odds, multiplied by itself and put the entries in an infinite square matrix, and then you can prove something about the sums and diagonals, and it all works out magically. Okay, so I promised you some results in interesting active field of research. So it turns out that that's related to random walks on slides. So hopefully I'll be able to make some isomorphism between what I promised and what will appear here.
You said you don't remember what you promised.
Yeah, so there'll be fuzzy isomorphisms. And I also can't promise whether I'll prove anything or provide examples, but it'll all become clear. So thank you to my collaborators amongst you for helping with this talk as well. So here's our model problem. Just arbitrarily suppose somebody in the world out there would want to give a presentation. Might seem like a stretch of the imagination, but just, let's enter this hypothetical world. And you yourself don't have the time. Whoever this person is can't do so. Okay. Like I said, there might be times where this could happen. So one model is the iterative model. Rather than having one other person make a full presentation, why don't we just sort of pass the work along? Seems natural. So we can formalize a space of slides, and within that space, a vector of such objects would be called a presentation. And yes, absolutely, I will formalize these notions. Certainly. Now we say random walk, but it's only so random because each step, each creation of each slide is deterministic based on the previous one, but overall we would interpret it as a random process, because who the hell knows what's going to come out of it. Okay, and we're looking for some sort of convergence. And again, that's a fuzzy idea for now, which I will certainly make formal later. But we're looking for some sort of limit object that will be a coherent presentation. First thing I'd like to make formal is the notion of a graph, because this will absolutely come up many times and you've never seen it before. So you can think of it as a subset of V choose 2, where V is the 22nd letter of the alphabet, and the height of the letter E is 2 inches. Take a minute for you all to read this.
It's a /pause for future reference.
I didn't know it was allowed.
This was me. I didn't know it was allowed either.
Oh.
You should have inserted pauses.
Yeah, I should have.
So already we have some indication of how sensitive to the initial conditions these kind of convergence problems are. Okay, so all we're going to do here is make some definitions. Which you can very plainly read, so there's no point in me reciting them for you.
Recite.
Can you give us some motivation?
Oh, absolutely. Of course. Certainly, being the operative word.
So shouldn't this be a directed graph? Because
It says diagram.
It does say digraph. So,
I should
cotton,
read.
sir.
There's a lot to read.
Okay, so thinking of how a presentation might go, we do want this to be a directed graph. There is some order, and if you take the same vector and apply the slides in different order, you get a different level of coherence. So we want this relationship we're defining here to be ordered in some sense, and we want it to be non-looping so that I don't stand up here and talk for an infinite amount of time and find myself returning to the starting slide. That's this condition here. So just assigning the ordering, sort of an element of this vector, a vertex is a slide, and we have a prerequisite relationship where if one comes before the other, prerequisite. And a presentation is just a way to go through the vertices in this graph in a particular way.
So do you have to walk, you don't have to walk along the edges then? You can just go from any vertex to any other vertex as long as the prerequisites are satisfied?
As long as that edge is there, you would be allowed to make such a step.
Well, the edges define the prerequisites.
Edges define the prerequisites. Right, but like let's
Oh,
say there's 3 slides in my talk.
Okay.
Okay, or three slides in the universe. And so there's the
Already
first...
a ludicrous notion.
Okay, well, simplified model. So you have the root slide, the title slide, I guess, 2 others, right?
I don't see that here yet, but okay.
Okay, well, let's just say you have a graph and it's got 3 vertices, 2 edges, right, and they're both coming out of the same thing. Then the only way to do this would be to start with the root, and then to go to one, and then to go to the other, even though there's no edge there.
So I think,
By all means. It's good to see fellow experts in the audience.
I think the requirement that the presentation be a walk in the graph requires that there be an edge.
So then how would you give a presentation on that graph?
That presentation would have to be 2 slides, I believe. You would sort of have an extra slide that does not belong to that coherent
Oh,
presentation.
okay.
If you were to
Okay.
include it,
Okay.
it would not be
So
coherent.
that'd be
If you look
non-complete,
down.
non-complete, okay,
Yeah.
okay.
A very natural notion, I think. We can agree on that. So, just to reiterate what came up there, we want every slide that's in our sort of space of slides to actually come up. That's the complete property. And we don't want to see anything twice, because that would be incredibly boring, so we don't want to do that. And there's just this, I forget what you call this on a directed graph, but if you have a prerequisite relationship, then certainly the first thing should come before the other. Okay. Now, such a graph that you mentioned would be a complicated one, because there is no coherent presentation that can be done.
Yes.
So,
See, that's why you put that definition in, to handle that case.
yes. And of course, the one that we are giving is very much coherent and not complicated. I'm just clarifying that from the get-go. So we don't need to preamble this with any lemmas or anything. We're just going to jump right into it. So imagine a talk graph where we have countably many vertices.
Wait, can you tell us how to pronounce that name?
As it's spelled. And this is a very old result. So people have been giving talks for at least 83 years, as far as I understand. So this is one of the earlier considerations. So if you have countably many vertices in your talk graph, then there exists a coherent presentation. So it's nice to know that given a certain setup, there is some way to actually present your slides in a nice way that people will attend and enjoy.
Where is the theorem from?
I want to say Hungary. Probably Budapest even.
This is coming across.
Yes.
Not
at
enough
least 3
doohickeys.
If he were here, he'd be pissed.
If you were here, he would have stormed out. Okay, so it turns out that the sort of proof for this is an algorithmic construction, where you're essentially looking for vertices that, well, at first we'd have to pick one to start with. And if there's some vertex that has no prerequisite, so we couldn't have gotten to it any other way, we should start there. So sort of remove that from our graph, look at amongst all the other vertices, is there another vertex with that property, and just keep adding them on and on until it works. So, okay, maybe you can't do that, but if you can, then you've succeeded. That's what the parenthetical says. It's not guaranteed to yield anything, but if it does, then it worked.
If it does, then it did.
Yeah, that's what I said. I said what I said.
That was Spielrein's lemma that wasn't listed on this slide. If it does,
then it did.
Yes.
Spielrein.
Obviously.
Yeah.
Okay, so for almost all of the ways that you could go through this algorithm, though, you will sort of break the prerequisite condition. We end up with the
Are we entering a loop?
yeah. So
We're traveling
it's a directed
backwards
route, but every
along
edge
the
goes
edge.
both ways.
Okay.
But you're only allowed to go backwards a finite number of times.
But then it's
Yeah, you're not coherent right now because you just went back.
It appears that I've lost everybody in the coherency. So let's just do a little time travel, and now we're back where we are. So most of the ways that you'll go through this, you will end up with a sort of non-coherent one because the prerequisite condition will fail. Okay. But it's nice to have this theorem out there.
I have a question.
Yes.
Is there an easy example of a talk with uncountably many slides that has more coherent presentations?
Sure. Imagine you had one slide for every real number.
Okay.
Because all of them are interesting and special.
Right.
Certainly there are infinitely many lines of certain slope through the origin. So you could have a presentation corresponding to each line. But like, for example, here I'm going to present to you all of the real numbers on the line y equals x. And I would start cycling through.
I thought coherent presentations had to be Hamilton.
Say again?
Well, they are. Every line goes through every real number.
I don't think this algorithm yields. It doesn't actually follow the edges.
Well,
But if it works.
I think that's the problem. Is that it doesn't follow the edges, so it's not guaranteed to actually give you a presentation. But if the edges happen to be there, then you've succeeded.
You should publish that. You've disproved his theorem.
Yeah. There may be maybe you've discovered a flaw. I mean,
Well, I suspect we're going to see the proof of the theorem on the next slide. So.
I would think so too. So let's see that proof.
Question answered.
Clearly there's something faulty with the projector. That slide was there, but we've lost it. So instead, let's just assume that worked and talk about the uncountable case. So his student, I believe, Natwork, which has nothing to do with Cantor, I don't think. It goes completely against what I said a minute ago. So I'm glad I put out that example to catch you all and to keep you on your toes. So thank you, Will. By the way, how do you integrate x? I'm going to meet on the next slide, so I had to ask. Okay. So we're going to do this by contradiction and assume that we do have a coherent presentation with uncountably many slides. And all you need to do is look at a countable subset, and certainly it too has a coherent presentation. Just because of the way the prerequisite relation is set up.
Yeah, that's cool.
So now just do this over and over, and after every time that I've removed countably many slides, there's still uncountably many left. And by a standard result in the field known as the concatenation limit, this ties together nicely, and we can't concatenate that many presentations over and over and complete all the slides. And I have run out of things to say. Illustration back now. Okay, so I believe what we want to talk about now is maybe a demonstration of these ideas, an example of some kind. So in particular, we're going to visualize this proof within some kind of diagrammatic example. So we have an uncountable presentation here. Now suppose we had that coherent countable sub-presentation right here. Now we want to extend it over and over by, in fact, concatenating. Right? So here we've done it twice. You can imagine that keeps going. If only I had a better mathematical description of what kind of process this is, I could tell you, but concatenation lemma is really all we have at our disposal. And of course we appeal to that fundamental result of cardinality, which is a countable union of countable sets. It's countable, it's just, I've heard somewhere that it's just the most important result in cardinality ever. So therefore,
so is there any analysis of this in the choiceless context? Because you're assuming choice.
I believe that's used in the proof of the concatenation lemma. But I don't remember exactly how.
If you don't assume choice, then how would this work? I mean, maybe using the determinacy, you can get a strategy for concatenating and there's still coherent presentation.
I would assume that without choice, you wouldn't even be able to start with a coherent subset.
You could probably assume Zorn's lemma or well-ordering principle, right?
That is choice.
Playing along.
So, without choice, you don't get two identical presentations? Two copies of... Never mind.
Yeah, I don't quite understand what you use choice for here.
This statement we have
I think that was proven in 1958.
Countable presentation and split up the slides, and you get two presentations that are similar to the original one.
So I think what actually happens is, if you have no choice, then all presentations are coherent. Because you don't have any choice over what to do. Everything is coherent. And in a way, nothing is coherent either. So it's a very bad universe. This is why we like choice. Okay, so now maybe we'll actually get to that example that I believe we were getting to. And I've fooled you all again. So as it turns out, I do not have a choice in this matter. And let's in fact consider what happens when we remove the axiom of choice. Kudos to whoever among you kept their mouth shut during that discussion, knowing this is coming next. So as we pointed out, that result that we appeal to at the end does not necessarily hold here. And in actuality, try it. So without that assumption, it's consistent that the real numbers are a countable union of countable sets. Okay. And so this is clearly left as an exercise for the listener. And of course brings up a question that must be on everybody's mind, including my own here. May or may not be right now or the next slide. Let's actually address this. So we've been joking about it. Let's be serious. I told you so. So I don't even need a title for this slide. So answer no. That's all you need. Okay. So if there are any set theorists, or logicians, or even probabilists here, we all know that there is a standard probability space over ZF without C, which is where we're living right now. So just consider it. Consider it. And I'm being very sketchy here, I'm aware. That's why I've labeled it as a sketch. Okay, so just take a model from that distribution. Fine. So this was originally brute force calculated, I believe, in the 70s on some heavy computer machinery. But that's been simplified somewhat, but it still doesn't seem to be any way to avoid lots of multiplications, additions, and I bet there's even some division in there. So I'm just going to label it heavy calculation and spare you the details. But the point is that the probability that our theorem is satisfied in the model is strictly less than 1, so by the standard probabilistic method, it worked, so it did. Okay. So that was just a sketch, of course, but hopefully you see the importance. So, it's in that probabilistic consideration that we lose constructivity. So let's approach this from a different angle and try to produce such a model.
So what does polynomial mean in this situation?
Bear with me, I'm going to loop again.
Polynomial in what?
In the inputs of the size of the problem. Yeah. Which is very great. So it's going to have to be, let's see. Polynomial in T. For time.
Yeah.
So again, no title needed. The answer is yes. So okay, to produce this model that satisfies the theorem, we're going to use a linear program, because of course all presentations are linear.
Yeah.
Okay. So we have an indicator variable, it looks like, based on whether one element is an element of another. Seems like a natural thing to do. Let's see where this goes. So take a standard enumeration of the axioms. Order does not matter here. And certainly no repeats are allowed. And so for each axiom, consider the size S of M. The number of constraints indicated by these variables is polynomial in M. And I think it's on the order of like S to the 100 or so. So it computationally infeasible, but it's polynomial. So for example, one thing you might want to specify for some very important reason that will be made known later is that if you want A in B, but B not in A, we just require this constraint, so that at most one of those conditions can hold true. And it seems like a very natural condition to have, so that's what I pointed out. Now, considering all of these constraints across M, the matrix of indicator variables is unimodular. And what that means is that we're building towards one presentation. There's only one module that we could possibly present. Now, because of that, just by something that everybody knows about optimal solutions of LPs...
for unimodular matrices.
Yes, for unimodular ones. The optimal, most coherent presentation amongst this has this problem. Which is how we set it up to begin with.
And that way you'll get an actual integer model instead of a fractional model.
Yes,
right.
That's an important thing to note. So having these constraints means that we're really only looking at integer.
You don't want
so from the
A to be
constraints you
halfway
couldn't have,
down.
yeah.
Right. Which is, of course, allowed without choice. Sometimes you can have half a choice.
Yeah.
Marla, I believe you had a comment?
No.
there any questions at this point? Yes.
You might want to fix it for the semi-even stuff. There's a typo in.
Oh, I'm sure there is. Where?
Polynomial.
No, that is not a typo. That is not a typo. Yes. Yeah, there are very different sizes of m that we could refer to, and they all have different names. It's a polynomial. I understand your confusion. Any other questions?
Are unimodular matrices square?
Yeah.
Why would we? Why is it obvious that these matrices are square and unimodular?
Why wouldn't they be?
It's obvious they're unimodular.
Okay.
In fact, it might be totally unimodular.
I think that's still open.
Oh, okay. So what would that imply?
Let's find out. Finally, we're getting to that example that I've been promising. So, okay, we've guaranteed already that the optimal solution obeys some integer program. And here we see that that solution, in fact, is just the product of all these indicator variables. Yes, clearly that is the case. And it has to be in this lattice D here, where D is the dimensional size of M. Just one of those names for size that we can...
Yeah.
In the polynomial.
Exactly. And here we have clearly ended our proof by showing
A box.
that we have negated the possible black hole that would have erupted if this proof were false. Okay, so let's just look at the simplest possible case, 3 dimensions. And now, I'm not sure if you can read these...
I'm confused. We're still looking for a solution for a coherent presentation.
So I haven't well beyond that. Come on.
Is the graph like naturally like embedded into that?
So I brought up the idea of convergence earlier, and we haven't made any claim about how fast that is. So it turns out that for many presentations, you could probably think of some examples that convergence to a coherent presentation is quite slow. But eventually, asymptotically, it does get there.
Maybe you sometimes get the feeling that he's not going to convert?
Quite often. In fact, an earlier lemma of the Hungarian man is that you can often have like wild divergence for a long time before obtaining convergence.
Yeah, I think his result only implies any concrete bounds on convergence as the number of slides goes to infinity.
So, and here we'll find out what happens as the number of slides goes to 13. So here is an illustration of the proof idea from the previous slide in just 3 dimensions. Except there is a typo that has been, in fact, pointed out in the slide.
To say that makes no sense.
So I believe this here is the 0.5 on the left. That should be a 0. But modulo that typo, everything is clear. So for this particular proof, and I think also this example, the author was awarded a Fields Medal.
Despite the typo.
Yeah, I actually think it was in part because of that. It's a revolutionary idea at the time. Even now. Actually, I think the typo is also in Fields. It's F-E-E-L-D. It's a different metal. Okay, so it also led to a natural question, letting the dimension go to infinity. So, of course, that has to be what we're going to find out about next.
Oh, that's the asymptotical conversion you were mentioning.
Yes, exactly. So you can see how we're starting to model that convergence. So what we'll do is start with that three-dimensional figure that we saw last time. Except let's project it onto a one-dimensional. Where here we're sort of iterating over D equals 3. Because naturally we start with A equals 3. So in a way what we're doing is considering the space of symbols that could appear in a presentation. Now, what happens when D equals 4? You can already sense some tension. And you can all predict what might happen when we let it be 5. There is, already there is some tension, and now there's definitely some problems. And when D is 6 and 7, clearly this process has to end at some point. So to address D's question here, if we iterate this over and over, asymptotically we're looking at big O, which we're allowed to use because this one is little o, of ABC, which are clearly separated from the rest of the process, plus the remainder, and so on. You'll bear with me sweeping some details under the rug here. And it turns out we can just collect all of those later terms into the standard Smasheroni constant, asymptotically speaking. It is. There's actually a dish named after this gentleman. Oh my God! Sorry, I didn't mean to reveal that.
Does this have anything to do with the ABC conjecture?
Yeah, I believe that the ABC conjecture implies this result, but I don't know if it necessarily goes the other way. In particular, this result has been around for at least 40 years or so you'd think somebody would have thought to use it already. I think part of the problem is that it's the ABC conjecture, not the ABC donjecture, which would make it much easier to apply.
How old is Smasheroni today?
What's that?
Smasheroni, how old is he?
He was a contemporary of Euler, whence the hyphenation. Except he was a very short man, so his papers are written very densely, as you can see. Okay, so this is a theorem. We may or may not prove this.
What?
Oh God. No, we don't prove it. We do prove it. Sorry, I entered a wild loop myself there, so I've emerged better for it. So, if you're unfamiliar with this standard technique of presentation theory, proof by quest, and it goes thusly. There are 2 doors, like any good hallway, and one of the guards is guarding the proof, and behind the other one is certain death. So we have to be careful, because we know one of them always lies, and one of them tells the truth, but we can't be clever, because that also leads to certain death. Or at least fatal stabbing. And at this point...
Has it been proved this? Has it been proved that fatal stabbing is a strict subset of death?
Yes.
Okay.
Yeah. I believe that's covered by the ER Chicago Hope. Other questions on this clearly demonstrable proof?
Well, what's
What kind of cat is that?
what's the question that we ask?
Is that Misha?
That was it.
That was uncoherent.
You spoiled my reveal, and that is the very question we would ask. What is the question we will ask? And that, of course, reveals the quest and the proof.
Oh, sorry.
That box.
Thank you.
The final slide, or are you thinking a lot for his proof technique?
No go a lot. He isn't responsible for that proof technique.
Oh, okay.
But he is one of the more renowned researchers in this area. The proof by quest area, anyway.
Okay.
So that's your original mascot? The pet that solved the proof?
What?
The animal there.
Yeah, the allot.
The what?
This is the allot.
Oh.
And I'm thanking him. And I would show you some references, but this in fact came from all of us in our brains, so there's no point in doing that. I'm not sure whether you have any questions. Feel free to fire away.
Why is he sad?
That's just actually how his face looks. They've evolved upside down, so he's actually smiling above his eyes. But he just looks like it.
That's why he's sad.
It's a tragic figure.
What did we prove in the end?
I demonstrated. It really didn't prove anything, unfortunately. But I gave you an example of that wild divergence followed by rapid convergence. As n approaches 13.
Now, if you wanted to, find like a hypermodular transubstantiary trigraph inside the sesquinormal equipartition, how exactly do you go about computing the facets of the Smashroni polytope?
Remarkable insight, Brian, to ask such a question. I think it was was it Nartok? I think first addressed that. I think it follows a similar constructive idea as the linear program thing, but you actually get a nonlinear program, which makes it vastly harder to solve, of course. And there have been various probabilistic ideas that have been applied on that, which are somehow still constructive. It's a remarkable field. And I think at best they've established some bounds that a presentation of that form would have to be somewhere between 1 and 1 million slides, something like that. But that's I think that's the best note.
And so then it's just an easy search through the space.
Easy in some sense.
Yeah. Okay.
Can I offer another answer to Brian's question?
Oh, sure.
The proof is trivial just bijected to a computable post set. Elements are non-singular, unbounded fan-in circuits.
Oh,
I think they're fan-out because of the direction of the presentation.
Well, they're bounded fan-out, but they're unbounded fan-in.
Good point.
All right. Well, let's thank Alot again.